Hey pre-calculus, I've got some more algebra related review for you guys. Section 1.2 is going to be all about exponents and radicals. I had some tech issues where I couldn't project the textbook problems actually on the screen, but I think the directions are pretty simple enough that we can forego that. So, let's talk about exponential expressions. Number 3 from the textbook is going to be my first example. What we're given is an expression where they give us negative exponents inside of a fraction. Now, obviously, if we had a calculator, we could just straight up do that, and it would probably give us a nice decimal approximation, or even a fraction if it's got a fancy function for that. I'm looking more towards the concept, though. All right. So, if you guys have your textbook, you should go to page 19, where it gives you a theorem about negative exponents. The theorem states that a, so any base a, to the negative m power over b to the negative n power, they essentially prove that this is equal to b to the positive n on top, a to the positive m on the bottom. All right, they do kind of a little proof of that. But bottom line is, if you have a negative exponent, it's literally just saying, through computation, this really impossible task of taking something times itself a negative number of times just needs to be rearranged, and then it makes sense. So how does that apply here? Well, 2 to the negative 3, and you know what? I'm going to just separate this a little bit by saying, let's say that this is in a different fraction altogether, like this. All right, hopefully we're okay with that. We're multiplying it. A negative exponent needs to rearrange itself to the other part of the fraction. So technically 2 to the negative 3 over 1 is the same as 1 times 2 to the positive 3. It just switches locations like you see over there. And then this disappears, and sort of like the leftover is going to be a 1 up there. Same thing happens over here. This is now 3 squared up top, and then we have to put a placeholder on the bottom there, so it's 1. I really wanted to highlight the fact that the 1 on the bottom and the 1 on the top, if they don't have a negative exponent, they shouldn't really move around, okay? So that gives us 1 times 1 times 3 squared, which is 9, over 1 times 2 times 2 times 2 times 1, which is 8. And there's your answer. All right, moving on, let's talk about number 7. Number 7 gives us 9 to the 5 halves. All right, quick bit about fraction-based exponents. Sometimes they call them rational exponents. This is really just telling us, again, you can't multiply something by itself 5 halves times in a row in the sense of how we normally think about multiplying things together. This is just sort of like a shorthand version of saying the top represents the power of this base as it's nested inside of a root where the denominator of this fraction represents what root you're actually taking of. You probably remember doing this back in Math 3. So we're really talking about the square root, so how many pairs come out of 9 to the 5th power. Now again, I want you to be able to do this without a calculator, so to speak. And when you think about it like that, you can think about this as, all right, I'm taking the square root. Remember, you don't need to put the 2 if it's just the square root. It's 9 times itself 5 times. And the whole idea of a square root is what times what gives you the number inside the root itself. So you can start taking out pairs. The square root of 81 is 9. The square root of another 81 would be multiplied by 9 again. And then when you think about 9, the square root of 9, an individual 9, would be 3. So it's 9 times 9 times 3, which ends up being 81 times 3, which 80 times 3 is 240. 1 times 3 is 3, so it's 243. Moving on to number 9, This one always seems to scare people when you see it right off the bat. You've got a decimal taken to a fractional power. So again, no calculator necessary, or not no calculator necessary. Let's say we're doing this without that as a tool. I think the best idea in this case is to, first of all, change it to a fraction. So this would be, okay, tenths, hundredths, thousandths. It's -8 thousandths. Remember, you can do that. And it's squared, because the top represents the power, nested in a cube root. So this is interesting. Think about this. When you square a number, hold on. 8 over 1,000, let's just reduce that to its simplest form. So we got a little aside here. -8 over 1,000, just start cutting them in half. Half of 8, 4. Half of 1,000, 500. Still even, keep cutting them in half. Half of 4, 2. Half of 500, 250. Still both even. Keep it going. Half of 2 is -1. Half of 250 is 125. All right. So inside of the square is the cube root of -1 over 125. And you know what? Instead of keeping the square as it is, I'm just going to write out times -125. So squared is the thing times itself. Now the first thing I notice is that -1 times -1 is just 1. Positive. And then 125, I don't have a calculator to do 125 times itself. I'm sure I could expand that whole expression. It might take a little while. But I'm noticing that 125 is actually a product of 5 times 5 times 5. You could go over here and use your factor tree and say, 125 divides 5. And 25 divides 5 times 5. There is a triplet of 5s here and a triplet of 5s here. So this is like 5 times 5 times 5 for the first 125. And 5 times 5 times 5 for the second 125. Now the cube root, instead of taking pairs of factors out, now you're taking triplets of factors out. So, well, first of all, if you have a fraction, you can change this to the cube root of the whole fraction is the cube root of the top divided by the cube root of the bottom. I just wanted to clarify that first. So the cube root of 1, what times itself 3 times gives you 1? 1 times 1 times 1. So the top is 1. The bottom, you can start just taking out triplets. So this is going to be 5 times 5, 25. So your final answer is 1/25. All right, and I'm not saying that's the only way you can do that. Some of you guys might be looking at this and thinking like, okay, that took you a long time to do. You probably could have done it some other way. Fair enough. Let's talk about number 17. So number 17 starts incorporating variables. And I think I see an exponent that registers as 0. That's kind of weird. Can't multiply yourself times something 0 times. In the sense of just basic ideas about exponents. So you got 6x cubed squared over 2x squared to the third power times 3x squared to the 0 power. Now, first of all, if you are a power or a group like an expression that's taken to another power, you could just rewrite it as 6x cubed times 6x cubed. But the shortcut is the 2 gets applied to both the 6 and the 3 by multiplying by whatever exponent is there. So there's that's 6 to the 1 power. There's 1 6 there. So it's 6 squared. That's 36. And this is x cubed to the square. So it's 3 times 2 gives me x to the 6. Similarly, on the bottom, you could do 2 to the 3rd power, which is 2 times 2 times 2, 8. Over x to the 2 to the 3, that's x to the 6. And, just exploring this a little more independently over here, if I distributed that 0 to both 3 to the 1st power and x to the 2 power, that actually makes the 3 now 3 to the 0 power, and x also to the 0 power, because 2 times 0 is 0. Now, the funny thing about the 0 exponent is that it's kind of like this weird anomaly that comes up when you try to apply the actual rule of division of exponents. And actually, it conveniently occurs right here so that I can actually show you how that works. So how it works is, there's a rule that says if you have x to the 6 over x to the 6, one way in which you can do that is just say, I could expand this out by saying it's x times x, like 6 times. But technically, it's the same thing divided by itself. Anything divided by itself is 1. Okay? I think most people are pretty cool with that. But the property for shortcuts when it's not the same number here is that you subtract them. So you'd say that x to the 6 over x to the 6 is technically x to the 6 minus 6. Well, what's 6 minus 6? It's 0. So x to the 0 power, I kind of showed that it equals 1 because anything divided by itself cancels out and you get 1 on the top and 1 on the bottom. So that pretty much is extended to any 0 exponent. 3 to the 0, that's 1. X to the 0, also 1. All right, so it's this whole expression times 1, plus we just showed that x to the 6 over x to the 6 basically cancels out to 1, and you're left with 36 over 8, which will reduce down to, cut it in half, cut it in half, cut it in half, cut it in half. 9 halves or 4 and a half. All right, I'm going to try another one here. Yeah, we got some time. Let's just do one of these deals. So number 25. What happens if you have multiplication and then there's a negative exponent that's being applied to the outside of it? Well, first of all, you're still going to apply the 4 power to both parts here. This is going to be 3 to the 4th power, but this is just 3 times 3 times 3 times 3. That's 81. So 3 to the 4th power becomes 81. Y cubed to the 4th power becomes y to the 12. Remember, you're multiplying those exponents. 4 to the negative 3, I'm just going to leave that as is right now, because again, you can't really take something times itself negative 3 times and come up with a legitimate value just yet. At least in my mind, a negative exponent doesn't make a whole lot of sense. This one's easy. You just say it's y to the positive 6th power. Now, the 4 to the negative 3, remember, in that previous example with the negative exponents, we moved it to the opposite part of the fraction. So right now we're kind of assuming that, hey, this is sort of like an imaginary fraction with a 1 on the bottom. So we just move 4 to the negative 3 to the bottom, thereby making it positive, which 4 to the 3rd power is actually 64. So I'm just going to change it to 64 right now. All right, from there you can use the commutative property to move the like terms side by side. And I actually misspoke when I said like terms. I should say the common variables, so the constants next to the constants, which actually creates 81 times 1 over 64. I just did that computation there. Here you'll notice that it's just going to be addition when they're multiplied together. So it's not going to be 12 times 6, it's going to be 12 plus 6.